In this video, we're going to look at Le Chatelier's principle, which is basically a way to determine if we disturb equilibrium, which way will the reaction shift to restore equilibrium. As we saw in the previous video, or as we talked about, when we mess with equilibrium, the reaction will want to go back to equilibrium. And the ways we can change our reaction to throw off equilibrium is to change the concentration of reactants or products, change the volume or pressure, and change the temperature. All right, so let's first talk about adding or removing reactants. So let's say we have a system at equilibrium, and let's say we're adding to the reactant side of the equation. And we have to add something that's actually in the equilibrium equation itself. So some questions to answer for this. How will this affect the rate of the forward reaction? So if we add reactant, that means we have to take that reactant and make more product to restore our KEQ, so the forward reaction will speed up. Therefore, the reverse reaction, going to products to reactants, will slow down as we have an excess of excess of reactants. K will not change. The only thing that changes K is temperature. Okay, how about this time we remove a reactant though? How will the rate of the forward reaction change? The forward reaction will now slow down. If we remove reactant, we have to convert some of our product back to reactant. We don't want to lose more reactant, so the forward reaction will slow down. The reverse reaction to make reactants will speed up. And again, K does not change unless with temperature, so K will be unaffected. And just here's some pictures of that going on, Le Chatelier's principles. So we have N2O4 goes to 2 moles of NO2, it's reversible. So if we add more of NO2, which is being shown here on this graph, what will happen is that the system will respond by making more N2O4 until equilibrium is reestablished. Again, the value of K will not change, but the concentrations will change to make the value of K again. That is the ratio of products to reactants equal to K. And so if we add NO2, then you can see that NO2 is used up, and it's used to make N2O4 until the concentrations are the same, or not the same. The concentrations don't change anymore, and equilibrium is reestablished. All right, so let's talk about changing volume now. So let's say we're at equilibrium and then we decrease the volume of our system. How does this affect the concentrations of solids, liquids, solutions, and gases? Well, solids, their concentration is not dictated by the volume that they're in. Either are liquids and solutions. So solids, liquids, and solutions. If you change the volume of the chamber, it does not change. For example, let's say I have 1 liter of water in a 10-gallon jug. Okay, let's say I take that 1 liter of water and put it in a 5-gallon jug. Does that change the volume of water? No. Does that change the concentration of water? No. But for gases, it does change it. If you shrink the container that a gas is in, you're shrinking the volume. If you're shrinking the volume and not changing the number of moles, because remember, concentration is moles divided by volume, your denominator just got smaller, so your concentration got bigger. You have the same moles of gas in a smaller volume. So gases, as the volume decreases, concentration will increase. Pressure. Well, the pressure of solids and liquids aren't affected by the container they're in, but gases, they are. So remember, for gases, pressure is just how often it hits a wall. If you're in a smaller container, you're going to hit the wall more often, and therefore your pressure will increase. All right. How does this affect the value of K? The only thing that affects the value of K is temperature. So K will not change. All right, so let's look at volume change in equilibrium. So decreasing the volume of container. For gases, it increases the concentration, increases their partial pressure, but does not change the concentration of solutions. So if your partial pressure increases, then the total pressure in the container will also increase. And so in Le Chatelier's principle, we want to move away from this increase in pressure. So the way to reduce pressure is to reduce the amount of gas molecules. So if volume decreases, the way the equilibrium is going to shift, it's going to shift to the side with fewer gas molecules. Because as we decrease the volume, we increase pressure. We want to negate that increase in pressure, so we do that by making fewer gas molecules. So let's take a look at an example problem for this, right? So we're at equilibrium for A, B, and C, and we change the volume. What is going to happen to the reaction? Is it going to shift right, shift left, or no change? So I2 to 2I. So 2 moles of I to 1 mole of I. If we increase the volume, we decrease pressure. Therefore, to make up for that decrease in pressure, we're going to make more gas molecules. So we're going to shift to the right. All right, B, 2 moles of gas versus 3 moles of gas. We decrease the volume, which means we increase pressure. We want to fight against that increase in pressure. So we're going to shift to the side with fewer gas molecules. That's the left. And here, 1 mole plus 1 mole, 2 moles and 2 moles, volume is decreased. Nothing happens though. No change. Because the amount of gas molecules on the products and the reactants are the same. So by changing volume, you actually don't change the position of this reaction. So what happens when you add a gas to a system at equilibrium? And if you add a gas and it's a reactant, it's going to shift your equation to making products. So let's say you have H2 as a reactant. You add more H2. You're going to try to get rid of that H2 and make more products, right? If you add a gas that isn't in the equation, well, it's not going to be in your KEQ. So adding an inert gas like neon doesn't do anything to your reaction. So it's only gases in your KEQ. Right? And let's take a look at this in pictorial form now. So here we have an increase in pressure for the reaction of N2 plus 3H2 goes to 2NH3. You increase pressure by decreasing volume. You're going to want to fight against that pressure increase by making more 2NH3. You do the reverse. You lift the piston. You remove that pressure. You're going to make more gas molecules. So it's going to shift to the left now. And that's it for this video. I'll see you in the next video.